So this time I'm going to talk about structured prediction with local dependencies. And the main thing we're going to talk about here is conditional random fields, and specifically the neural version of conditional random fields. And these are really useful for a variety of tasks, but mostly sequence labeling. So if you're interested in sequence labeling, this is a very good thing to know about and use, because most state-of-the-art models use some variety of this. So yeah, as I said, sequence labeling is going to be our example. There's lots of different sequence labeling problems, like part of speech tagging and named entity recognition. For the first one, we're labeling one tag per word. For the second one, we can label spans, but we do this by something like a BIO tagging scheme, where the beginning of a span is marked with B, in the span is marked with I, etc. So as I talked about before, one way to do this is with sequence labeling as independent classification, where you basically take in the various words surrounding this sequence, and then you put each of them into a classifier and classify like this. So as an alternative to this, I talked about methods like teacher forcing. So in teacher forcing, or kind of sequence models, you take in your previous prediction and you feed it into your network as you make your next prediction. And so these are another method that we use for sequence labeling. And sorry, my equations disappeared. You see blank spaces where my equations used to be. But basically, independent classification models, to contrast these two methods, independent classification models basically have these very strong independence assumptions. So what you're doing is you're assuming that given, if you want to predict I, you can write the probability of Y as the product of the probabilities of all of the things. So each of these are independent of each other. So as I mentioned last time, or the time before last, I believe, you have no guarantee of this giving you consistent structures. So you won't be necessarily getting a good consistent solution for your entire sequence. On the other hand, history-based models, sequence-to-sequence models, models using teacher forcing, these have no independence assumptions. So instead, we model according to this equation, where the next one is conditioned on our input, and then all of our previous decisions like this. Right? So this looks familiar, right? This is what we talked about before in sequence-to-sequence models. So the problem with this is that it becomes very difficult to calculate exactly. So we need something like an approximate search algorithm, like greedy decoding or beam search or something like this to get the best example. Also, if you train using something like teacher forcing, you get problems of exposure bias or label bias. If you train with something like reinforcement learning or structured prediction, suddenly training becomes a lot harder. You can't enumerate all your hypotheses. And for difficult problems, then you need to do pre-training with maximum likelihood, which might be suboptimal, for example. So just to summarize, number one, the model is too weak in a way. For number two, the model is too strong. And it's too strong so that you can't efficiently enumerate over all your answers. So a solution to this is kind of something in the middle, or something that can be useful is something in the middle. And these are models with local dependencies. So they don't entirely say that every prediction is independent, but they also don't say that we're going to condition on everything else in the sequence. And one example of this is conditional random fields, which I'll be talking about in a moment. In conditional random fields, they have exact and optimal decoding and training, and you can do this with basically a dynamic programming algorithm. Specifically, it's something like the Viterbi algorithm, which I believe people have done in algorithms for NLP, if you took that, right? So I'll assume that you kind of know this, and then just reiterate the main points. So as review, conditional random fields are kind of in the framework of globally normalized models, which I talked about before. So globally normalized models, each sequence has a score, and based on that score, we can calculate the probability of a sequence by adding up the scores for all of our possible hypotheses and renormalizing. And the exponent of the score here is also called a potential function, which you can write as psi. And basically, if we take the score, exponentiated score of the potential function and renormalize, then we can calculate this model. So this is good. We talked about these before and explained some reasons why these are better from the point of view of exposure bias or label bias than other models that we could use. But of course, the problem here is that we can't calculate this denominator exactly. So what conditional random fields do, there are other models with local dependencies, but conditional random fields are maybe the best example of them, is basically they calculate scores based on only a subset of the decisions that you make. And by doing this, you can make your scores, you can more easily calculate your scores in an exact way. So one important thing is the general form of conditional random fields or globally normalized models is you can calculate these the scores over the entire sequence. So if you look here, we have these scores over the entire sequence, and this is not making any independence assumptions, right? This is not saying that y. This is not saying that y is independent of all the others. In order for y to be independent of all the others, you would basically need to approximate this score. Approximate this score with the sum of scores over all the elements in the sequence. So in this general framework here, this could be used to express a regular sequence-to-sequence model, so it's not making any assumptions. Well, this one could only express something like this. So this is making kind of independence assumptions here. So if you write the kind of general form, you have x that can influence all of your labels, y1, y2, y3, all the way up to yn. And then all of the labels can influence each other as well. So you have connections basically between all of them. And and this gives you this score here. And then what a CRF, and more specifically a first order linear chain CRF, is the specific type of CRF does, is they say only tags that are directly next to each other in a sequence labeling problem can influence each other. And all the other tags, based on, given y2, the decisions over y1 and y3 are not influencing each other. And this is kind of a graphical model format if you study graphical models, but that's less important. And then based on this, what you can now do is you can now say the score the score is now in the middle of these of those two options. So for one, our score was over all of the output. For another, our score was only over a single one of the outputs, and we added them all together. In the linear chain CRF, in the middle, now says our score is over these pairs of outputs. So you can see it's significantly relaxed from this because now we're only considering pairs of tags, but it's not quite as relaxed as this, where you were only considering tags individually. So is this clear here? Any questions? Okay. So this might also be reminiscent of HMMs, for example, if you've done HMMs before. CRFs are not new to neural methods as well, so even if you haven't done them in the framework of neural methods, you might know about these to some extent. But yeah, that's the summary here. So then how do we calculate these potential functions, or how do we calculate these scores? So basically, we can calculate a score for every transition, where the score is the thing inside the exponent. If you take the exponent, you can turn it into a potential function, either way, whichever one you prefer. So here we have two different elements to this. The equations may look a little bit scary, but basically this is a transition, and this is kind of an emission score. So the transition score is the score that we can use to calculate the how likely two neighboring tags are to co-occur with each other. And the emission score here is just how likely is this tag going to be to appear in this sequence, or according to this input. And you'll note here that the emission score here is basically this independent thing. So when we turn it into a CRF, we're basically just adding another element that we can additionally use to score based on the interaction between these. So these T's or S's can be calculated according to a neural network. They might be an embedding based on our context or something like that. So for when we incorporate neural features, basically what we would do is we would have some sort of features calculated according to our neural network, fx at position I. And then we would have a parameter matrix that was specifying our transition between y, I minus 1, and I. We would have another parameter matrix that would say how likely is yi here. And the idea behind this is that basically you could say, given this context, how likely am I to do this transition? Given this context, how likely am I to output this particular tag? So the problem with this here is the number of parameters. So if you look, this is the size of the vocabulary. This is not the length of the target sequence. This is the size of the vocabulary squared times the dimension of the, or basically times the size of this weight matrix, because we need one for every tag transition, right? So if we think, let's say we have our embedding size, which is 512, and then we have, let's say we have 100 tags, just kind of arbitrarily. Maybe we have a part of speech sequence with 100 types of tags. Then we have 100. This will basically add, let's see. Is that 505 million? Okay, there we go. Yeah, there we go. So it would add 51 million parameters to our model, and this is quite a few. Parameters to be adding just to capture transitions between tags. So what's very common to do is to say, okay, this transition is not dependent on the context. So this transition is not dependent on the context that we're in. So we just cross out this 512 and don't condition on this, and instead just have 10,000 transition parameters that say how likely are these tags to appear next to each other. And this can capture things like maybe a noun is very likely to come after a determiner, or a determiner is not likely to come after a determiner, etc. And now we have y size of the tag set y squared parameters plus y times the embedding size, which we use for the second. Are there any questions about this? Yeah.
In the first one, why don't we use the features of y I minus 1 also? Like in the first equation, it has function of y minus 1, and in the second, it doesn't.
So why don't we use the features of y I minus 1? That's a good question. And the answer is normally. Let me move to this figure here, and the reason why is because normally when we do when we calculate this fx, we calculate it with some basically complicated neural network model like a bidirectional LSTM that can pick up the information about the things next to it in the first place. So basically, to summarize, putting a CRF on top of your independent model. On top of your independent model here, requires that you add only 10,000 parameters to your model, which is not a whole lot. It's not compared to your LSTM or all the other things that you're using. And it allows you to very simply calculate the interaction between tags. So this is kind of a popular method, especially for sequence labeling, but also for other tasks as well. So this kind of black ball here is expressing our CRF that takes in features from the purple vectors and then does a kind of structured inference algorithm over this to calculate your final decisions. And I will talk about the structured inference algorithm in a second, but are there any questions so far? Yeah.
So, like in the original CRF literature, there is a lot of work with, say, skip connections across CRFs.
Uh-huh.
So, are they generally used, or do we just use them by?
So when you say skip connections, you mean like
Across
skipping
labels.
from previous labels? I haven't seen this. These are, I guess maybe the most common thing to call this is higher order CRFs.
Yeah.
So higher order CRFs basically don't, they aren't this first order linear chain CRF. They actually have lines between things that are not directly neighboring. I haven't seen this very much in neural models, and the reason why is probably twofold. Number one, they're slower usually because they require you to consider more things in the past or the future. Ones with skip connections are a little bit better than other ones, but so they're more complicated, they're slower. And the other thing is you're pretty much hoping that your BILSTM will be able to pick up on the long distance dependencies anyway. So just the directly neighboring ones are the ones that are more useful. One very interesting thing that one very useful thing that I'm not going to cover this time is semi-Markov CRFs. In semi-Markov CRFs, basically what they do is instead of looking at individual words, they look at spans, and then they try to decide whether a span is good or not. And those have been used with neural models. So that's good because you can incorporate features of the whole span, like let's say, how many times has this span appeared in my corpus? And if it has appeared frequently, it's more likely to be a named entity. Or is this span in Wikipedia or something like that? So That's something I have seen, but I haven't seen stuff with skip
Another
connections.
thing is, does it have to be a linear chain, or can you use like a dependency parse to choose which label you want to condition on?
So that's a really good question. So does it have to be a linear chain or can it be a dependency parse? It can definitely be a dependency parse. There are CRFs over trees. So anywhere where you can do a dynamic program and calculate neighboring labels, you can use a CRF. So if you can write a dynamic program over trees, which you usually can, then it's possible to do this. Any other questions? Okay. So then the next thing is training and decoding of CRFs. So when I first started NLP, I remember I was always very scared of CRFs because I'm not very good at taking derivatives. Or at that time, I wasn't very good at taking derivatives. Now I'm a lot better at taking derivatives because you need them for neural nets. But so it used to be that training CRFs was significantly more involved than it is now. And I'll explain why in a second. Actually, within neural networks, it's really easy to train CRFs compared to what it was before. So the way you do CRF training and decoding is basically we know that our CRF looks like this, where each where the probability of each sequence is the probability of the product of its potential functions. Or you can take the sum of its pairwise scores and then exponentiate it afterwards, either way. And we're dividing by z of zx, which is our partition function, which is the sum of the basically potential functions over all of the sequences. So during training, the most difficult part is computing this partition function. So the top one, it's pretty easy, right? We already know the correct sequence. So all we have to do is step through the correct sequence and calculate this for all of them. But for the bottom one, we have this big sum over y, which is what we've been trying to avoid in all of our structured training algorithms up until this point. So in order to train calculating the partition function is the hard part. And then once we calculate the partition function, we can just use this as our loss function in our neural network. So like everything else in a neural network, if we can calculate a loss function, backpropagation in our neural network library will do everything else for us. So our goal is to basically calculate this efficiently. For decoding, what we want to do is we want to calculate the argmax of p of y given x. So in order to do this, we'll have to find the sequence with the maximum value, maximum score, basically. Yeah, and this is exponential, so this is difficult. So if we look at the various interactions in our model, each label depends on the input and the neighboring labels only, the labels next to it. But given the other adjacent labels, the others don't matter in making our decision. And if we knew the score of every sequence, y1 to y of n minus 1, it makes it easy to calculate the score of the sequence y1 to yn. And the reason why you can see from the above graph here, or above equation here. Actually, no, sorry, you can't see this from the above equation here, but you'll see in one slide. So basically, what we need to do is if we know all the scores for all the sequences leading up to this point, then we can calculate the scores for the rest of the sequences. So the way we do this is basically exactly the same as the Viterbi algorithm, with one small difference. So if you remember, the Viterbi algorithm is a dynamic programming algorithm where we step through forward and then calculate backward. And we actually use the Viterbi algorithm to solve the argmax problem, here. But now we don't want the max solution. Instead, we want to know the sum of all the solutions. So what we do is first we start out, let's say we want to say natural language processing is a science or something like that, and we want to calculate the score of its, or the partition function for all of the sequences. So we have our transition score here, which is calculated according to the sequence, according to our parameter. So we have our 10,000 parameters, and we calculate the score of the transition based on these. And then we also have our emission score here. So this actually, sorry, these are from some old slides, and these are from kind of like HMM land, where we actually had conditional probabilities for all of these. But just think of this S as the score that I mentioned. Sorry. Think of S as the score that I mentioned down here. It's this, this emission score right here. So we calculate it by taking the feature function calculated by our neural network and multiplying it by a vector over all of our tags. And we can do this, of course, for every tag. So this is our vector of emission scores, and this is our vector of transition scores, given that the last tag was the start of the sequence. So then we step onto the next. Tag, and if you remember from the Viterbi algorithm here, what we did for the next tag was we took the score of all of the previous tags at all of the previous positions. We added our new transition scores, we added our new emission scores, and then we took the max, if you remember from the Viterbi algorithm. So the Viterbi algorithm, we just want to calculate the score with the highest value. What we don't do the max here. What we do instead is we take basically the sum of the probabilities, or if we're calculating in log space, we take the log sum x of the scores. Do people know about log sum x? Some people. So basically, the idea is when you have probabilities, if you have p of x and p of y, p of x or y is equal to just the sum of these, right? So what log sum x is when you're calculating in log space, you take your log probabilities of p of x and y, so these are your inputs to your log sum x function. Then you take the exponent of these, and then you add them together, and then you take the log again. So basically, this is just summing things together, but when your probabilities are in log space. One thing you should know about this is if you do this in the simple way, if you just do this like within your neural network and you're calculating things over an entire sequence, you might get numerical underflow problems. So if this log p of y is a very big negative number like this, and you take the exponent, suddenly it becomes 0. And your neural network training, or your training of your model breaks. So my best suggestion is to just use the log sum x function implemented in your neural network or numerical toolkit. But if you really want to do it yourself, what you also do is you take the max. You take the max of the two inputs. Of x. And you subtract the max before taking the exponent. And then you add the max back in after reverting it to log space. So this is a trick you need to do if you're not using the built-in log sum x function. But if you use the built-in log sum x function, don't worry about it because somebody's already thought about it for you. So based on this, then we take this value, and that's our score of now and at the next time step. And then at the very end, we to calculate the partition function, usually at the very end, we have a transition to a final state, the last state of the, and we sum up everything resulting in our transitions to the final state. And then this is our partition function, basically. So the probability is the probability that we go over all tag sequences and then end up in the final state. And that's how we can calculate this. Are there any questions here? No? Okay. So, so this slide was made by Max last time. It has lots of equations on it. I think it's good if you want to go back and look at how you calculate this exactly. But I will skip that because it has too many equations. But you can go back and review it later if you'd like to take a look. Another thing I should mention is that all of these, you can do these as vector or matrix operations. So if you want to do this is vector or matrix operations within a neural network toolkit, you can do that as well. So I said at the very beginning of this section that it used to be very intimidating, or more intimidating to do CRFs than it was than it is now. And the reason why is because before, what you had to do is you had to do the forwards pass, then you had to do an identical backward pass, then you had to calculate the marginal probability of each transition between the tags. You had to sum all of them up, and you had to calculate your gradient manually. But luckily now we have PyTorch, we have DyNet, we have TensorFlow or whatever. And basically all of these, they calculate gradients for us. That's what they do. So now all you have to do is you have to calculate the partition function, you have to calculate the score of the correct hypothesis, and then once you've done that, you just plug that in as your loss function. The log probability is your loss function into your neural network toolkit, and it will automatically do the backward pass for you. So yeah, that's about all. And as I mentioned before, once you have your parameters trained, all you have to do is instead of calculating this log sum exp, you calculate the Viterbi algorithm, use max instead, and you can get your best overall result. Are there any questions? Yeah.
So this is assuming you want to maximize the log likelihood loss, right?
Yes.
But if you wanted to do something like a rank loss or a hinge loss per se, could you do the same with the Viterbi and then backpropagate through the Viterbi?
That is a good question. I guess there's kind of two answers. If you have another loss function, I'm actually going to talk about that at the very end. You can also do Viterbi, and if you have local independence assumptions, you can do the Viterbi algorithm, and you could do something like penalizing each correct answer, like for a large margin structured hinge loss or something like that. And it's actually easier to do here because you can do exact search than it would be for a sequence-to-sequence model. So actually that's very useful in these models. And basically everything I talked about 2 times ago, like last Tuesday, applies here as well. So, any other questions? No? Okay. So there's a case study for this, just to kind of demonstrate why this is useful. This is kind of a state-of-the-art model for sequence labeling made by Max Ma here at CMU. And basically the idea is you would like models that work well for basically any sequence labeling task, and you don't want to you don't want to engineer them too heavily by designing feature templates, et cetera. And the model is relatively simple. It's something that you can already do with the stuff that you learned in this class, plus the stuff that I'm talking about today. And the idea is that you have a character level representation of words with a convolutional neural network. And then you have a bidirectional LSTM plus CRF on top of this character level model. So the character level representation basically is a CNN over characters in the sequence. And you pad to make sure that you capture all of the characters in the sequence. And you run a trigram CNN over these to get representations, and then you do max pooling over these representations. So it's like a feature extractor over the characters in the sequence. And then this character representation is concatenated with a word embedding. So one thing you should know about character representations, if you want to use them in your models, is often they're not adequate on their own. Often they're not enough to efficiently express words. So it's most effective when you use them in combination with word embeddings. So the word embeddings capture the information about your high frequency words, and the character representations help when you don't have enough training data for your word embeddings. This is especially important for something like named entity recognition, where in named entity recognition, the low frequency phenomena are the ones that really matter because they tend to be entities. So then you run a bidirectional LSTM on top of it, and then you have a CRF layer on the top that enforces consistency between the tags. So like anything else, optimization is important. So parameters are important. SGD with momentum. This could probably be substituted for atom or something else like that. Learning rate decay. So as I mentioned before, you reduce the learning rate to help prevent overfitting. You apply dropout with a fixed rate of 0.5. And parameters are initialized, and it uses word embeddings. I believe this paper tested different word embeddings, and the glove word embeddings tended to be the best, but there are new word embeddings methods out now, so the newer ones might work better. So kind of the analysis here is interesting. It's on part of speech tagging and named entity recognition. And basically, you can see that bidirectional LSTM with no character embeddings does kind of okay on part of speech tagging. You get significantly better by considering character embeddings. And then if you add a CRF on top, you get a little bit better for part of speech tagging. On the other hand, for named entity recognition, the character embeddings are really important, and then the CRF layer also contributes on top. So whether you need something like a CRF is kind of problem dependent. If you have something where really there's lots of correlation between the tags, and you have low frequency phenomena that you would like to capture by modeling these correlations, then something like CRF is important. So that's it for the local dependencies part. In summary, CRFs are nice because they are a good trade-off between the complexity of training a full sequence-to-sequence model and the naivety of training a model that considers everything to be independent. So if you want to do something where you can write a dynamic program easily, I definitely recommend doing something like this. Are there any questions before I move on to the next one? The next one's kind of totally different. So. No? Okay. So I talked about reinforcement learning before. So reinforcement learning is one method for considering rewards in models. So we have lots of reward functions in structured prediction, like for part of speech tagging, we might want token level accuracy. For named entity recognition, we might want F1 score. For dependency parsing or something, we might want a labeled attachment score. For machine translation, we might want a blue score. And all of these are not equal to maximum likelihood. So I've talked about a bunch of models to incorporate these. And if we think about how our different reward functions impact our decisions, I guess the question is, do these impact the optimal decisions that we're going to do? So if we have data 1, which is distributed according to some probability distribution, and we want to predict y given our input, and we have other data that's also identically distributed, and we want to predict y given x. But we have a different reward function for these two. Is our optimal policy equal or not? So I think the answer is probably relatively clear here. Who thinks they're equal? Or who thinks they're not? So the answer is not. If we have a different reward, our policy is different. And you can think of a very simple example. So let's say we have a predictor that basically says, how is there money in this box? And the chance of money being in box number 1 is 0 or $1 million. And we have another predictor that says there's a probability of 0.2 that we have money in the second box and the value is the same. Which one do we pick? It's pretty obvious. Who says number 1? It's not a trick question, so so then you pick number 1 and then you're happy. But let's say we put $1 billion in number 2, in box number 2, maybe or $0. So now our predictor says 0.8 probability on the left one, 0.2 probability on the right one. Which one do you pick? Who says number 1? Who says number 2? So this is a difficult economics problem, actually. So there's a thing called marginal utility. As you get more money, it becomes less attractive to you. So this actually isn't completely clear, but let's say you just wanted to maximize the expectation of the amount of money that you would get. Let's say money was linearly associated with happiness, which I think is not the case, but let's say it was. If that was the case, then obviously the answer is pick number 2, because your expected amount of money is $200 million for the second one, and for the first one, it's $800,000. So we've talked about a bunch of other methods to consider reward or risk of doing things like max margin or reinforce, also reward augmented maximum likelihood. But one thing I've told people, you should be using reinforcement learning sometimes, but not all of the time. This is one example of when you shouldn't be using reinforcement learning. So one example of when you shouldn't be using reinforcement learning is when you can trivially enumerate all of your hypotheses. So if you only have 10 choices and you can exactly calculate the reward for all of them, randomly picking one of those choices, seeing whether you get a reward, and then feeding it back doesn't seem to make a lot of sense. You can just calculate all 10 of them. And once you can calculate all 10 of them, you can exactly calculate something called a risk function, which is basically the expectation of your error for picking a particular hypothesis. So P of y prime given x is the probability calculated according to your model, and your error is y prime is calculated using y prime in your correct answer. You can also do your expected reward, which is kind of like the opposite of your risk. Your risk is your expected error. Your expected reward is this expectation of this, and is the expectation of the reward. And then you can directly use this as your loss function. You don't need to do any sampling. You don't need to do anything complicated like that, or baselines or whatever. Now the problem is we can't enumerate all of our hypotheses most of the time. But there's an effective method where basically instead of enumerating all of our hypotheses, what we do is we sample a subset of the hypotheses that we could be outputting, and we take our probabilities. So we have our probability for each hypothesis up here. And we renormalize. So we take, again, all of the hypotheses. Sorry, that selection is not working very well. this one down here. And so let's say we randomly sampled 3 hypotheses, one where the probability is 0.3, 0.2, and 0.1. What we would do is we would divide all of these by 0.6, which is the sum of all of the ones that we actually sampled to get our probability. And then we would use that as our loss function. So this has been used in things like machine translation. It's relatively nice. The advantage of this compared to reinforce or something like this is explicitly only considering the differences between the hypotheses in your samples. So if you have several hypotheses that are very similar, it will basically push the better ones up and the worse ones down without actually changing all the parameters related to the things that are the same. The disadvantage of this is it's much more conservative than reinforce or something like this. If you only have one sample, it won't do anything because basically you'll be multiplying 1 by your error, and 1 by your error doesn't give you any information about your model. So you need multiple hypotheses, and even then it will be more conservative than something like reinforce, which is actually updating all of the parameters of your model that were involved in generating this hypothesis here. So this is just another option. If you find reinforce or reinforcement learning things tend to be unstable, this is something that's just as easy to implement and tends to be more stable. Yeah.
Where is the set S coming from?
The set S is sampled from your current probability distribution. So you would randomly sample outputs according to your tagging model or your sequence model or something. Yeah.
So you could apply this to something like this, just like basically sample the traversal through.
So you could apply this to a CRF, but you don't need to. So one of the beauties of the CRF is you can exactly enumerate all of your hypotheses. So you don't actually need to do this. Although the one caveat is that you might want to do this if you have a loss function that isn't decomposable according to the dynamic programming structure of the CRF. So, there's a few tricks that go into optimizing this that are written in the paper. So one thing is they remove identical hypotheses. That's absolutely necessary. Another thing is sometimes they include the true hypothesis in your sample space all the time in order to make sure there's at least one good hypothesis there. They also do a thing where they exponentiate the probability here to make the distribution more peaky or less peaky. So if you're interested in the details, you can use this. But I like this method myself. It has worked well for me in the past. So I think it's worth considering.
How is this connected to importance weighted sampling? Is it roughly the same thing?
How is this connected to importance weighted sampling? As far as I know, it's not. So importance weighted sampling, basically what you're doing is you're sampling from one distribution and then you're renormalizing to match another distribution. In this case, we only have one distribution.
You're trying to match the original data distribution, right?
Right, and just sampling can actually directly match the original data distribution as long as we can sample exactly from our model. And for things like sequence models, we can sample exactly from our model using ancestral sampling, like I talked about before. So importance sampling is a nice concept if you want to do something like generate samples from one model, but it's too hard to generate them from that model. So you sample from another model and reweight, but I don't think it's directly connected to this. Any other questions? Yeah.
Applications where this is useful, you said machine translation apart from that.
This has also been used in things like semantic parsing with latent variables, where you have like a latent structure that describes the semantics of the sentence, and then based on that structure, you get a reward of some sort. This can be basically put in anywhere where you would be using a reinforcement learning type thing. It's just a different way of calculating, of optimizing your reward. And I think in the end, they actually both are doing more or less the same thing. It's just how do you approach it? And this tends to approach it in a more stable, more conservative way. Yes.
Why just reinforcement learning? Because this is essentially weighting the loss corresponding to each term by some weight, and that is uniform in the normal case, right? So it's a more general paradigm.
I'd actually say reinforcement learning maybe is a more general paradigm. This might be a subset of reinforcement learning methods. But in the end, algorithms like reinforce are actually trying to optimize this, but the problem is you can't enumerate over all of them, and you can't necessarily get a reward for all of your action sequences. One thing is this will only work when you can run on the same example multiple times. So one example of reinforcement learning where you can't do this is like, let's say, a dialogue system. So a dialogue system, you can only interact with the customer once. So you can't actually calculate multiple samples for a particular input. You can only calculate one, and if that's the case, you need something like reinforce, and you can't actually use this because, as I mentioned before, this only works when you can get multiple samples. So that would be one example where you can't use this method. You can only use it when you can calculate multiple things for the same input.
Unless you are training on a user simulator.
With a user simulator, yeah. So that's the great thing about user simulators for dialogue. You can do whatever you want. So. Any other questions? No? So one final thing that I wanted to mention was that you can also do this token-wise. So let's say you want to, let's say you have a risk function where basically you really don't want to mistake a preposition for a determiner. You're a little bit better about mistaking a preposition for a verb phrase, and you're pretty okay with mistaking a preposition for a noun for whatever reason. So if this is the case, you can actually calculate the risk for each value, and calculating the risk, doing a minimum risk objective over this is as simple as just calculating the probability for each of the tags, and then taking a dot product with your error function for each. So this is, people will do this without even thinking about this, like minimizing the risk. But basically, this is reweighting. This is reweighting each of your decisions based on how bad that decision is, and this can be very useful if you have an idea about which decisions are good and which decisions are bad. You can use this in a CRF model, as I showed here. You can also use it in just a regular BILSTM tagging model with no structured prediction whatsoever. So this is good because it's definitely more efficient than sampling and stuff like this. So this is a good match with CRF style models as well. So that's kind of fast for today, but are there any final questions about this? Okay. That will be it for today. If you're considering sequence labeling, think about using CRFs as the takeaways.